Unit 1B, Lesson 2. This will align with Lessons 4.1, 4.6, 5.3, and 5.4 in the textbook. Again, this is going to be dealing with proofs. So the standard proof theorems about triangles. These theorems will include measures of interior angles of a triangle summed to 180 degrees. Base angles of isosceles triangles are congruent. The segment joining midpoints two sides of a triangle is parallel to the third side in half the length. The medians of a triangle meet at a point. The first theorem we are going to discuss is the triangle sum theorem. This theorem says the sum of the angle measures of a triangle is 180 degrees. It does not matter if it's scalene, if it's right, equilateral, obtuse. It does not matter what type of triangle it is. The three interior angles will always add up to 180 degrees. Now we're going to go through a proof that shows why the triangle sum theorem is always true. So our given is we have a triangle XYZ. What we're trying to prove is that if we add angle 1 plus the measure of angle 2 plus the measure of angle 3, that sum will be 180 degrees. Alright, so again, we're going to do a two-column proof. Our statements and our reasons. The first thing we're going to do is, we know we start with a triangle. We're going to construct line YA parallel to XZ. So we're going to construct this red line YA so that it is parallel to XZ. And all we're going to do is call that a construction. So we're constructing that line so it is parallel to side XZ of that triangle. Next thing, number 2, we have the measure of angle 4 plus the measure of angle 1 plus the measure of angle 5 is equal to 180 degrees. So if we add these three angles together, we know they form a straight line as we go around. We talked about this earlier, that a straight line is always going to be 180 degrees. And this is a form of the linear pair postulate. And this is something we will discuss in class. There's actually another part to this we should discuss and add to this proof, but we'll just talk about that in class. That's the linear pair postulate for step number 2. Step number 3, we have angle 2 is congruent to angle 4, and angle 3 is congruent to angle 5. Well, if we constructed this line so that it is parallel to XZ, we have two parallel lines cut by another line. This is acting as a transversal. And if this is a transversal, that means angle 4 and angle 2 are alternate interior angles. And the same with angle 5 and angle 3. If we treat this as a transversal, YZ, angle 5 and angle 3 are alternate interior angles as well. We know if two lines are parallel cut by a transversal, alternate interior angles are congruent. So the reasoning for this, those are alternate interior angles. Now step 4, we have the measure of angle 2 equals the measure of angle 4, and the measure of angle 3 equals the measure of angle 5. That is just the definition of congruent angles. If two angles are congruent, if angle 2 is congruent to angle 4, then the measures of those angles are equal to each other. And finally, we get down to step 5. Measure of angle 2 plus the measure of angle 1 plus the measure of angle 3 is equal to 180 degrees. Well, we're using a combination of step 2 and step 4. Since the measure of angle 2 is equal to the measure of angle 4, I can substitute that equal value in for the measure of angle 4, which is why from step 2 to step 5, this measure of angle 4 changes to the measure of angle 2. Because those two values are equal, we can interchange them. Same thing with the measure of angle 3 and the measure of angle 5. Since the measure of angle 5 is equal to the measure of angle 3, I can replace the measure of angle 5 with the measure of angle 3 down below. Okay, so now I have a measure of angle 2 plus the measure of angle 1 plus the measure of angle 3 is equal to 180 degrees. Those are the three interior angles of this triangle, and the reason for that is substitution. Okay. The substitution property of equality: if you have two equal values, you can substitute one of those values in for the other. So now we have shown why three interior angles of a triangle always have a sum of 180 degrees. The next theorem we are going to discuss is the base angles theorem. If two sides of a triangle are congruent, then the angles opposite them are congruent. So if we look at this triangle ABC, side AB is congruent to side AC. If that's true, then angle B is congruent to angle C. This is the base angles theorem. Another topic, this is called CPCTC. Corresponding parts of congruent triangles are congruent. So part of what we're going to do in some of these proofs coming up, if we can show two triangles are congruent, that means all 6 individual parts, the 3 corresponding angles, and the 3 corresponding side lengths must be congruent as well. That's called CPCTC. Now we're going to complete a proof for the base angles of isosceles triangles, the base angles there. So our given is side AB is congruent to side BC. We want to prove that angle A is congruent to angle C. Okay. So in this triangle, the first statement, just like the other ones, this is going to be our given. AB is congruent to BC. Step 2, construct angle bisector BD. So if you look at the picture towards the top, I constructed this angle bisector for BD. Okay, that means these two angles are going to be congruent. And like the last proof, we can just say construction. Now step 3, angle ABD is congruent to angle CBD. Angle ABD is congruent to angle CBD. That is simply definition of an angle bisector. So we know if we constructed that angle bisector, those two angles must be congruent to each other. Step 4, BD is congruent to BD. So now you can see we have two triangles that are formed. Okay, they share this common side. Well, if they share a side, that side is going to be congruent to itself. And that is called the reflexive property. Reflexive property says any side is congruent to itself, any angle is congruent to itself. Reflexive property of congruence. So now we've shown that AB is congruent to BC, angle ABD is congruent to angle CBD, and BD is congruent to BD. So now we can say in step 5 that triangle ABD is congruent to triangle CBD by the side angle side congruence postulate. And finally, we're to step 6. Since we know those two triangles are congruent, corresponding parts must be congruent. So we can finally say that angle A is going to be congruent to angle C, and that is CPCTC. Corresponding parts of congruent triangles are congruent. So now we've shown a proof that demonstrates that if two sides of a triangle are congruent, the base angles opposite them must be congruent as well. The base angles theorem. To end this lesson, we're going to discuss two more theorems and a few definitions. This first theorem, the mid-segment theorem. The segment connecting the midpoints of two sides of a triangle is parallel to the third side and is half as long as that side. So if we have triangle ABC, D is the midpoint of segment AB, E is the midpoint of segment BC. The midpoint means that E is exactly in the middle between B and C. The mid-segment is connecting these two midpoints. So what this theorem says is that DE is parallel to AC, and DE is half as long as side AC. Alright? You would also be able to construct mid-segments for the other two sides, and they would be parallel to the third side and half as long as the third side as well. That's the mid-segment theorem. Now we have three different vocabulary terms. We have the median of a triangle, which is a segment whose endpoints are a vertex of the triangle and a midpoint of the opposite side. That's a median. A point of concurrency is the point of intersection of three or more lines. And then a centroid is the point of concurrency of the three medians of a triangle. Okay, so three vocabulary terms to be aware of. The last theorem in this lesson, concurrency of medians of a triangle, which says the medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. Okay, so using this example, if we have triangle ABC, if we look at AD, this is a median of this triangle. It goes from vertex A to the midpoint of the opposite side. So this is a median. Side or segment BF is a median as well. It goes from a vertex to the midpoint of the opposite side. And EC is the third median of this triangle. It goes from the midpoint to the vertex. These three medians are intersecting. This is a point of concurrency, a point of intersection of three or more lines. This point of concurrency is called the centroid, the point where the three medians of a triangle intersect. This centroid will always occur inside the triangle. So if we look over here, if P is the centroid of triangle ABC, then AP is 2/3 of AD. So from this vertex to the centroid, this distance is 2/3 of the whole length of that median AD. BP is 2/3 of BF. So from the vertex to the centroid, this is 2/3 of the whole length of BF. And same for the third, CP is 2/3 the length of CE. So this is the concurrency of the medians of a triangle. Again, with all the proofs and information in this lesson, make sure you write down any questions you have over vocabulary terms, theorems, definitions, or anything regarding the proofs so that we can discuss these at the beginning of class.